So today we're pleased to have Linyuan Liu from the IAS, and she'll be telling us about equivariant cohomology of the affine Grassmannian and Ginzburg's picture.
Thanks. So the main goal of my talk today is to provide a link from Jize's talk last week to Anne's talk next week. So Jize talked about geometric Satake last week, and Anne will talk about visual canonical and Finkelberg's article on Derived Satake next week. So let me start with geometric Satake. So first a quick recall of the picture of geometric Satake. So as usual, let G be a reductive algebraic group over C, and let K be a field. So soon I will. So right now K is just a field, and soon I will assume that K is just SC, and G check is the Linyuan Liu group over K, which is the split reductive group with dual root datum. And recall this picture from Jize's talk. So we have this Satake category. Oh, sorry. Satake category, so which is GO equivariant power shifts on the affine Grassmannian, and we have rep G check and this Satake isomorphism. We know that so this map, the inverse of the Satake, so that I'm using here, is just taking the cohomology, and we have this forgetful functor and this. So this map, the composition of the forgetful functor and the inverse of the Satake correspondence is just taking the cohomology. And so this, the lower part of this graph is just the geometric Satake picture, and then so I can get upper half. So because the cohomology space, the cohomology of a sheaf is naturally a graded module over the cohomology ring of the affine Grassmannian. So naturally there's another half of this graph, which that makes the whole diagram commutative. And so with this picture, so Ginzburg asked two very natural questions. So first, since so by taking this functor, we just take sum of all the degrees. So naturally, there's a grading here. So what's the representation theoretical meaning of this grading? Which the sum as a vector space equals to V itself. And the second question, so what's the representation theoretical meaning of this action on V? So action of the cohomology ring. So these are two natural questions that Ginzburg asked from the picture of the geometric Satake. And so let me first quickly try to answer the first question. So from the I will give a more precise answer later. Basically this grading provides a morphism from rep G check to Z graded vector space, and which is compatible with forgetful functor. So by the Tanakian formalism, which is a theory that allows one to recover algebraic groups from their category of representations, we know that so this functor, so from rep G check to Z graded vector space, is just induced by a morphism of groups from GM, from C star to G check. So in order to answer the first question, so we know, so by this formalism, we know that so this grading should correspond to the eigenspace decomposition of a certain semi-simple element in G. And to answer this question, we just need to find this semi-simple element. And so from now on, I will assume that K equals to C. And many of the results in this talk will only work in the characteristic zero case. So to answer Ginzburg's questions, first we need to compute the cohomology ring of G. So let me first recall what a principal SL2 triple is. So principal SL2 triple inside the Lie algebra. So here, it's just a triple EHF such that the bracket HE equals to 2E, the bracket HF equals to minus 2F, and the bracket EF equals to minus H. So basically E equals, so equals to something like this for SL2, and H equals to 1 minus 1, and F equals to 0, 0, 1, 0, something like that. And so in my talk, I will mostly consider those SL2 triples inside the Lie algebra G check. So the Lie algebra of the dual of G. So let me fix this setting. But so this works for any semi-simple Lie algebra. And there are two important facts.
Sorry, if you want the minus sign, do you want a minus sign on F?
Here?
Bracket of EF is minus H instead of usual H.
Maybe.
For virtual roll down is EF equals to H. So I think it's just a matter of the sign.
Yeah, I need that. Thanks. Yeah.
And this is a definition of an SL2 triple, not of a principal SL2 triple.
Such that E is a regular nilpotent. Sorry. Thanks. I forgot this very important sentence. So set that E is a regular nilpotent element. And then there are two important facts. So first, the centralizer of E is abelian. So basically, the reason is that whenever we have a regular semi-simple, like a regular semi-simple X, is so basically the idea is that whenever we have a regular semi-simple element, the centralizer is always a Cardan subalgebra, which is abelian for semi-simple Lie algebra, and a regular nilpotent can be viewed as a limit of regular semi-simple elements. So this Lie algebra is a sort of a limit of those Cardan subalgebras. So it should also be abelian. And the second fact is the adjoint action of H stabilize this centralizer. And the second fact is just by Jacobi identity. And right now we are right now we can give a description of the cohomology ring of the affine Grassmannian. So proposition. So H, the cohomology ring of the affine Grassmannian, is just the universal enveloping algebra of G of the centralizer of any principal nilpotent. So different choices of principal nilpotent will give us isomorphic algebras. And so actually, so this is not only a isomorphism as graded algebras. It's also an isomorphism as graded Hopf algebras. So we know that there's a Hopf algebra structure on the right-hand side. So why is there a Hopf algebra structure on the left-hand side? Because so as mentioned, Ginzburg mentioned last week, the affine Grassmannian is homotopically equivalent to the loop space based loop space of the maximal compact subgroup. And so this is so in particular, this is a topological space. No, this is a topological group, and the multiplication of this topological group will induce a co-multiplication on this cohomology ring. So which gives it a structure of a Hopf algebra, and so there's also grading. So as graded Hopf algebras, the grading on the left-hand side is just by the degree of cohomology, and the grading on the right-hand side is induced by the eigenvalue of the joint action on that G check D. So where EHF is a principal SL2 triple. And so we can decompose this space with respect to eigenvalues, because this action is semi-simple. And the idea of the proof, so basically, so we can see that there are a lot of choices here, so E and H, and so let me quickly talk about the idea of the proof. So you can see that actually we can actually find this E. So from the picture I showed at the beginning, so there's a functor provided by the Satake correspondence from rep G to graded to actually modules on the cohomology ring of the Grassmannian. That is compatible with the forgetful functor. So by the Tanakian formalism, so there's a morphism of Hopf algebra from this Hopf algebra H star C to the universal enveloping algebra of G check, and so we just need to so first Ginzburg proved that this is injective. And hence we just need to find the image of this morphism. And second, Ginzburg proved that the first Chen class of the determinant line bundle on Gr, so we should be an element in H2. So it's a principal nilpotent. Which I will denote by E. So by some basic fact by some facts about cohomology rings of a loop group of a compact Lie group. So we know that the left-hand side is abelian, is commutative, also co-commutative. And hence, so since the image contains E, so it must be contained in the centralizer of E. So it factors through, so the image is contained in the in the universal enveloping algebra of the centralizer. And so this is 3 and 4. So this is isomorphism. So basically, these are the steps of the proof. And so this gives us the answer of a description of the cohomology ring of the affine Grassmannian. And right now we are ready to answer Ginzburg's question. So I guess so we already know the answer. So the grading on this space is just the eigenspace grade the decomposition of the action of H. And second, the action of the cohomology ring on V is just the restriction to the universal enveloping algebra of the centralizer. And Ginzburg proved more than that. This. So actually, so we have this functor from perf or Satake category to grade the category of graded modules over the cohomology ring. And the functor is just by taking cohomology. And Ginzburg proved that this functor is fully faithful. And I think this is quite miraculous. So for example, so because it means that a very small piece of G-check can determine the Hopf spaces. So let us first do a sanity check for G-check equals to SL2. So G-check equals to SL2. So this is just corresponds to restriction to the Borel. Generated by E and H. And so we know that so whenever we have a reductive group, the restriction to a Borel is always fully faithful. And but this so for SL2 is not so mysterious. But for general reductive group, it is at least very mysterious for me. And the second remark is the graded here.
May I make a comment?
Yes.
So I think that in general, you know that you have you have a homomorphism of over Borel of SL2. So therefore, it's a homomorphism over the entire SL2. But then this SL2 together with the centralizer just generates everything, the entire D algebra.
You mean for SL2, the centralizer generalizes everything?
That's right, because the centralizer is just all highest vectors.
Yeah, you mean the fixed point of centralizers are highest weight vectors?
No, the centralizer is just highest weight vectors inside of G for your
with
SL2.
respect to the SL2.
Yeah. So for SL2, the centralizer is just this.
Wait. I mean the centralizer of E inside of G is the highest weight vectors for the principal SL2.
The highest
so
weight.
Therefore, the F
yes, I agree.
applied to the centralizer just gives you the full Lie algebra G. So everything which is equivariant, every map which is equivariant with respect to H and the centralizer
Yeah.
going to be G equivariant. So I don't think there's a mystery here.
I still haven't fully understood your remark, but so yeah, because I was trying to give it an explanation on the representation theory side, but I couldn't. So let me try to think about your comment like during the break. So because I actually plan to ask this question here. So, but let me first make the second remark. The gradient here is very important, because if we remove it, then so the centralizer so just is contained in the nilpotent radical, and the restriction is not full. And so the third remark, I guess, is not that necessary. So I want to ask, so in general, how could we see this fact? On the representation theory fact, so on the representation theory side. So because, for example, for G equals to SL3, the centralizer looks like this. And so this plus H just determines the Hopf spaces. And I haven't fully understood why, but I'll think about the comments. And anyway, so this functor is fully faithful for some reason, and actually Ginzburg has proved even more. So right now, so you want to consider higher Hopfs. So actually, so this functor also provides bijection on higher Hopf groups. And so I need to make this precise, because the Satake, so I've already assumed that K equals to C. So the Satake category is semi-simple. So it makes no sense to talk about. So it makes sense, but the higher Hopfs are all trivial. So instead of higher Hopfs inside the Satake category, we should actually consider the higher Hopfs inside the derived category. So GO. Okay. So these things are in general, so there's no reason for this thing to be trivial. And this is the shifts constructible. For geo orbits. And Ginzburg, so to be more precise, Ginzburg proved the following theorem. So for each lambda mu in the co-weight lattice dominant of T, such that so these two fixed points corresponding a T fixed point are in the same connected component. Which means that the two weights are in the same coset by the root lattice, and for every integer z, we have a bijection. So the previous functor induces a bijection from this Hopf space, higher Hopf space in the derived category. From between those two IC shifts to this Hopf space, and I will explain to you in a minute. So and so here, so the notation not so good. So here, so the Hopf I on right hand side means morphism that, so because we are talking about graded algebras and graded modules, so Hopf I on right hand side means the space of morphism shifting gradient by I. And so use this result. Ginzburg gives an answer to a prototype of the derived Satake. So we have this picture. So we know we have rep G check and the Satake correspondence, and the Satake category, which is a heart inside this derived category. And from the derived category, we can take this cohomology, and it will be mapped into the category of graded modules over the cohomology ring, which is just the universal enveloping algebra of the centralizer. And so this part is something I already talked about. And then there's this mysterious thing, so that I don't quite understand how Ginzburg came up with it. So this is just so n is just the normal cone inside G check, and that's a nilpotent cone. Sorry. And this is the category of G check cross C star equivariant coherent shifts on this nilpotent cone, and so there's a natural functor from rep G check to this category. It's just by tensor product with the coordinate ring, and then once we have a shift on n, so we G check equivariant shift on n, we can take the fiber at over E, and we will get a G check. Yeah, so we will get a module over the centralizer of this element, and then so we know that these two categories are the same, and Ginzburg also proved that this K upper zero, so this composition is fully feasible. And so I call this kappa upper zero because during next.
Excuse me.
Yeah.
Fully faithful on what? On just the abelian category?
So yes. So this is from.
That's a composition. Sorry. Yeah.
Yeah, the composition. And actually he proved. So actually, to be more precise, this is what he proved, which is stronger. So home. I db go I see lambda I see mu is isomorphic to home I co G check cross C star n fr L lambda fr L mu, and what I just said is just by taking I equals to 0, and this is almost like a Derived Satake. And so as before, this means the morphism that shifts the grading by I. And okay, I think this is a good time for break.
Okay, we'll meet back at 3:35.
Like, so here should be A. You mean A, B, A?
Yeah.
Okay, maybe I made a mistake in the computation. Sorry. Are you sure?
It's the linear combinations of E and E squared.
E should be in there, right?
Oh yeah, you're right. So I sorry, you're right.
So this is maybe a stupid question, but there's normally when you do like G-equivariant perverse sheaves on the nilpotent cone, there's this interesting operation you can do where you take the Fourier Deligne transform and then restrict back to the nilpotent cone.
When you're talking about perverse sheaves?
Yeah, perverse sheaves, yeah.
Perverse sheaves on G-equivalent perverse sheaves on the nilpotent cone.
Yeah. So you're looking at G-equivariant coherent sheaves on the nilpotent cone in your picture that you drew?
Yes.
Is that right?
In my picture, I'm considering a G-check equivalent coherent sheaves on the nilpotent cone.
Yeah, so I was wondering if there was in the coherent setting whether you have this kind of
I have no idea.
operation of the.
Can anyone else answer this?
What's the answer to that? Should be all good.
Can I ask another question?
Yes.
So the determinant line bundle is canonical, right? Like it doesn't involve a choice.
So that part I'm not so I guess so. So I was trying to understand that. So I guess we are taking so I was looking at the book called Loop Group by Loop Groups and I think to define a determinate line bundle, we need another description of the affine Grassmannian. So it's the Grassmannian model of a Hilbert space, and I'm not sure. So how do you define a determinate line bundle on the affine Grassmannian?
I thought it was something like there's sort of a modification, and then there's like a finite dimensional vector space. Given the point of the Grassmannian, I can stick it inside
the real Grassmannian, the actual Grassmannian, and then there's a line determinant line bundle on the actual.
Yeah, just a whole one. But yeah, the reason why I asked is because I'm just I would have thought the first Chern class of the determinant line bundle was something canonical, but I didn't understand how a particular principal nilpotent gets picked out.
But it shouldn't be, it should depend on the choice because it corresponds to E under this map.
No, but there's also a choice of E. So E is just so right now E is just a principal nilpotent element. So there are many principal nilpotent elements.
That's why I'm confused because on the one hand,
yeah, you're right. So there might be choices, and I'm not sure.
I think
also,
the determinantal line bundle does depend on a choice. You choose a representation and then embed like an infinite dimensional representation and projectivize and embed your Grassmannian in that, or like pull back generator or line bundle. But there's a choice in the action on that representation that involves a similar choice to the choice.
So it's not just writing the affine Grassmannian as a union of usual Grassmannians or subspaces inside usual ones and pulling back the usual one from the Cook embedding, the usual O of one.
Maybe I don't understand something, but for me, affine Grassmannian is just a parabolic Flach variety for a Kosmody group. And at least on the usual parabolic Flach varieties, if you are in rank 1, meaning that the semi-simple rank of your levy is 1 less than of your ambient group, then you do have a canonical choice of a line bundle, which will be ample.
Maybe it's an isomorphism of the description of the cohomology of the Grassmannian, which is not canonical.
Yeah.
Sure, and another remark, so as long as as long as you decide on your SL2 triple, and you get your associated data, such as the element H and the centralizer, then you recover E canonically up to scale.
Yeah.
As unique element of degree 2.
Yeah. That is true. Yeah. Yeah. Also, so when we identify those this rep G check, there's also a choice here. So because we can just change it by any inner by any automorphism of G check. So I guess there are some. Yeah. I'm not sure if there's a choice there. So maybe I should start again.
Yes.
Okay. So right now I want to do some preparation for derived Satake. So the first question is, what is derived Satake? So I'm asking this because the Satake category is the GO perverse shifts on the affine Grassmannian. But we know that via the forgetful functor. So this is equivalent to the GO. So those perverse shift that are constructed with respect to GO orbits. So on the abelian category level, so these two are the same. So there are two candidates for the derived Satake category. So here we have the Equivariant derived category, and here we just have the derived category of constructible shifts. So which is what Ginzburg described. And so when we talk about derived Satake, which one should we choose? So of course the right hand side also makes sense. But so we are more interested in the left hand side because there's a this has a monoidal structure. So while the right hand side doesn't. So if we write down the definition of the convolution, so we will see that at one step we want to take the inverse of some pullbacks, and which only exist in the equivariant setting. And so which make so since this is so the left hand side is a monoidal structure, and the Grothendieck group, so which will make the Grothendieck group a ring, and after tensoring with C with the complex number, so we will get the Hecke algebra, C, GK, GO, GO, and so the left hand side is more interesting and has a lot of backgrounds in like geometric Lagrange program. And so Dreamfield has asked this question. So what is the monoidal category of Hecke algebras? So basically, this question almost so if we can give an answer to the derived Satake correspondence, then we can answer Greenfield question in some sense.
What kind of answer was Drinfeld looking for?
So basically, just so his question so basically his question is just to describe this monoidal category. So we can just yeah. So yeah, because of the left hand side has a lot of more interesting structures than the right hand side because of the monoidal structure.
You do get if you take direct sums of shifts of perverse simple sheaves, you're going to get an additive category that is monoidal. So what you want is a triangulated category. That's why you need a derived category. Is that correct?
Yeah. So we want a triangulated category with a monoidal structure.
Yeah, but you can have an additive one. That one just by taking perverse sheaves. The convolution is respecting the fact that you are a direct sum of shifted simples, but it's not. You want something a better structure.
Yeah, I want something better, but of course, so this question is also interesting, but not as interesting as this. and so we want to make modifications to Ginzburg's pictures. So this is the Ginzburg's picture I was talking about, and the modification I need is to replace this constructible category with the equivariant category. And naturally, so we want to replace the usual cohomology with the equivariant cohomology. And then this will be the graded modules of over the equivariant cohomology. And this is something we don't know yet. And so the first step towards an answer to this question is to compute this thing. And so we know that, sorry, not over a point now, of the Grassmannian. So we know that in particular, this is a module. This is a module over the geo-equivariant cohomology ring of a point, graded module. And so we can view it as a sheaf, a coherent sheaf. Maybe quasi-coherent, I guess. So anyway, so let's just add the quasi here to be safe. A coherent sheaf on this space T over W on this variety, and so after viewing it as a sheaf over T over W, so for any element in this T over W, so we can it makes sense to talk about the fiber of this sheaf. So the fiber of the cohomology ring of the equivariant cohomology ring of the affine Grassmannian over T, which will denote by H star T, the specialized equivariant cohomology. And so in Ginzburg article, so he didn't describe this ring directly, but he did describe those things. So Ginzburg described these fibers. And I will give Ginzburg's description. So let's consider the composition of maps. So on the right-hand side, we have G check star rec. Inside G check star, and maps to the quotient over G check, so by the co-adjoint action, which is isomorphic to T check star over W, which is also naturally isomorphic to T over W. And yes?
When you write a rec, it means all regular elements, not just semi-simple ones, right?
No. So yeah, so this is a remark I need to make. So in Mito, regular means those elements such that the joint action, so here is the co-adjoint action, has maximal dimension. It's not the regular that to define Cardan subalgebra. So yeah. So in that we need so here just the centralizer has minimal dimension, but in some books the regular elements means that not only the centralized, the generalized zero eigenspace has minimal dimension. So regular. So here is thanks for the remark. Here regular I mean any just those elements with maximal joint or such that the adjoint orbits has maximal dimension. Thanks for the remark. And so we have this composition of maps, and I will call this PR. And so for each element T here, it corresponds. So for each element T, so basically there's a factor. So this PR map provides a bijection between regular co-adjoint orbits in G check star and T over W. And so for each t on the right hand side, so it corresponds to an orbit which I will call OT, which is the corresponding regular co-joint orbit. And we can take elements in X, an element X in this orbit, and we can talk about the centralizer. Which is the Lie group of the centralizer of X in G. So if we identify G check star with G check via the killing form, so this is just the centralizer of X inside G check. So which is what I denote by this before. And this is this Lie algebra is abelian. And uniquely determined by the orbit up to canonical isomorphisms. Hence T. So up to canonical isomorphisms. And we denote so hence it only depends it is uniquely determined by T, and we can just use this notation AT to denote this universal abelian Lie algebra that doesn't depend on X in some sense, and so Ginzburg proved that. So this specialized equivariant cohomology ring of the affine Grassmannian is just the universal enveloping algebra of AT. And so remark, so when T equals to 0, we will recover our previous result. On the usual cohomology ring, after identifying so because so when T equals to 0, so the corresponding regular orbit is a regular nilpotent orbit, and we can just identify G check star with G check, and we will get our previous answer. And right now I want to give another description of this AT using constant slice. So right now, so let me identify G check with G check star by the killing form. And let EHF be the principal SL2 triple inside G check. And so we have this constant this subspace constant slice. So E plus the centralizer of F inside G check maps to G check over big G check, which is isomorphic to T over W. And so the composition map, the constant prove that the composition is a bijection, it's an isomorphism of varieties. And so for each T here, it corresponds, so by this isomorphism, it corresponds to a unique element here in the constant slice. I will call it XT. And then we know that, so the AT I just defined is just isomorphic to the centralizer of this XT. And so we can, so in this, So this is an isomorphism, means that there's a copy of T over W inside G check, or G check star in our previous picture. And we can, so in this sense, we can view this AT to be a sheaf on this copy, such that each fiber is just the centralizer. And so we want to remember our previous, so our goal right now is to describe the equivariant cohomology ring, and right now we only know the fibers. And so we want to globalize those fibers. So the Ginzburg's results globalize. And to get this thing. And so the idea is that there should be a sheaf on coherent sheaf on G check star rec, such that each fiber is the centralizer. So I will call this sheaf I, such that the fiber at each point C is the universal enveloping algebra of the centralizer. And so if there's so there should be a sheaf like that, such that so the equivariant cohomology ring of the affine Grassmannian is just the pullback as the restriction of the sheaf on this slice. On the cosine slice, which is a copy of T over W. And so this is just a rough idea, and to make it so right now we want to find a sheaf like this, and here's an exercise. So if we consider the map I defined before from G check star rec PR to T over W, and then let T upper star be the cotangent bundle on the right hand side. And then the pullback of this cotangent bundle of this symmetric power of this cotangent bundle. So pullback of symmetric power of this bundle satisfies our description of I. Which is means that the fiber is each fiber is the universal centralizer. It's the centralizer, universal enveloping algebra of the centralizer. Of I, and hence we so we can guess what the cohomology ring is. So this is a theorem by Bezukhnikov that is that was stated by these two people, but they claimed, as they say, that Ginzburg already proved it almost. So this equivariant cohomology ring is just the coordinate ring of the total space of the tangent bundle over T over W. And so there's also a symptotic version, so which describe. So they also describe this GO cross GM equivariant cohomology. So which is the coordinate ring of the deformation to normal cone of this diagonal inside T over W squared, which will be defined. I hope defined by next week. And we can get this result from this by taking fiber over 0. And right now, we are ready to describe Bezukhanikhov and Finkelberg's picture. So which looks not quite ready, but so at least part of them. So this is just the Satake correspondence that we are familiar with. And here, so this Satake category lies is a heart of this equivariant derived category, and by taking a equivariant cohomology, we get a functor to the category of graded modules over the equivariant ring. And on the left-hand side, so as the Ginzburg picture, there's this thing, the G-check plus C star equivariant coherent shifts on G-check star, and this map is just by taking tensor product with a coordinate ring, and then we have this kappa bar, so which send this category to graded modules of the universal centralizer shift, and which by our previous explanation, so are isomorphic to graded modules over the coordinate ring of the tangent the total space of tangent bundle of T over W, and by our computation of this equivariant cohomology ring, so these two are also isomorphic. And what is this? So this kappa is just the composition. And what is this? So
excuse me, should this be cotangent bundle instead?
No, it is tangent bundle. So in the exercise, it's the cotangent bundle, but it's sim cotangent bundle. So it's all tangent.
But the universal centralizer is a symplectic variety.
A symplectic?
I'm confused.
What? Sorry?
I always thought that the universal centralizer is a symplectic variety. I have hard time identifying it with cotangent bundle in my head.
Yeah.
But maybe I'm missing something.
I don't quite understand the question.
Okay, no mind.
So the kappa bar here is the restriction to the, so basically it is the restriction to cosine slice. And so we will recover the kappa bar, kappa up zero in Ginzburg picture by just taking the fiber at E. So this is how this picture that we will see next week related to Ginzburg's picture. I guess that's the end of my talk.
Any questions for Linyuan?
So can I ask a question? So I still haven't understood Ivan's explanation on the representation theory side about why that functor is fully faithful. So the centralizer of E is just the highest weight vectors inside G check. I agree.
Yes,
And
inside of G.
Yeah, I agree. And so some vector is so if some vector is fixed by this centralizer and by H,
it's also fixed by F. So everything which is fixed by E and by H is also fixed by F, as you have pointed out.
Yes, exactly. So because of the SL2 case.
That's right. And F and the centralizer of E just generate everything in your algebra.
Okay, thanks. So basically, so the SL2 picture is not that special. So the SL2 case explains everything basically.
Yeah.
Okay, thanks a lot. So.
I have a question. Could you go back to the deformation to the normal cone thingy quickly?
there's something I want to say. So the definition of deformation to normal cone used by Ginzburg, by Bezukhanico and Finkelberg is not the usual one. So so what's
the usual one? So that's okay. I was just thinking about the left-hand side for a sec. So as Ivan pointed out earlier, you can think about the I'm muted now? No. You can think about the affine Grassmannian as a Katz-Moody parabolic subgroup. Is this GO semi-direct product GM? That's the parabolic subgroup.
I don't know. Who can answer this question?
No, I think GM is like loop rotation, right?
Yeah. Look, so yeah, maybe I should say it because there are many choices here. So this is the loop rotation.
Because if not, I mean, this entire story should be more truly affinized by describing the p-equivariant cohomology of Katz-Moody group mod Katz-Moody parabolic rather than GO of DK mod GO. That sort of adds an extra variable to your polynomial ring. You're looking at TF modulo W finite. And you sort of have extra information floating around, which I think is extremely useful. And I want to see this whole story with that. This is my suggestion if it's not already there.
May I ask a different question?
Yes.
I somehow thought that when you add loop rotation, then your objects are no longer commutative.
Sorry?
And somehow I thought that the algebra of differential operators appears somewhere in this picture, but maybe I'm just missing something.
You mean there are differential operators appears in this picture?
Yeah.
So I'm not sure if it will help. It will help answering your question. So yeah. So after so B and F prove that there's a fully faithful functor here, and that link these two categories, and then we can consider the derived category of this thing, and we can degrade it. So there's a grading here, and we can degrade this category, and we will get so after degrading it, we will get the category of G-check equivariant DG modules over symmetric power of G-check, and the symmetric so with the zero differential, and that is the Derived Satake equivalence we should get. But I'm not sure if this has anything to do with your question.
No, I'm not sure either, but okay.
Vanya,
I have another. Can I ask a question?
Can I just make a comment based on Vanya's question, and then so I like basically if you'll get kind of non-commutative things if you add the loop rotation on the right hand side, then you get like Harishchandra bimodules and things like that.
You mean so if we add a loop rotation here?
On the exactly, yeah.
And yeah, here we will get Harishchandra bimodule, a symptotic version of Harishchandra, category of Harishchandra bimodules, and we will get yes. So yeah, I think I will talk about this next week.
Sorry, George.
Okay, yeah. So early in the lecture you mentioned that there was a question of finding representation theory meaning of this grading of this representation, but I think so. And you mentioned this work of Ginzburg, but it has been there's something earlier, something very similar has been done several years earlier by Gupta, something called Gupta.
Gupta.
Yeah, 1987. So namely.
Is this spelled like?
Namely, I defined for each wave space, I defined the Q. There's a Q analog of wave multiplicities. So each wave multiplicity was, instead of a number, was a polynomial.
Yes.
And there was a question about what interpretation does you have a representation theory, and Gupta found one, and using also regular nilpotent. So this was found many years before Ginzburg. But in that case, it was a filtration of the wave spaces. Giving this various powers, coefficient of powers of Q. But it sounds very similar. I'm sure it's almost the same.
Sorry, so it's Gupta Catholic. So it's it's Gupta's Brzezinski.
Yeah. Later she changed her name to Brzezinski.
Yeah, she changed her name after getting. Yes, I know that result. So that result is purely on the representation side.
But it answers the same question. It answers. It gives a representation theory meaning of this grading.
I agree.
And using also regular nilpotent, but in a different way.
Yeah. So whenever we have a regular nilpotent that is compatible with the torus that we use for the weight decomposition, we can define this this filtration.
Yes. And the other remark is that I think in Ginzburg paper, you have to be careful that I was told by several people that the proof of commutativity is wrong. I prove that you can that if you take the convolution of two of these perverse sheaves, you get perverse sheaf. That I proved. Yes. But I couldn't prove that it was commutative. And Ginzburg claimed that he proved it, but apparently this was not good. And only Dreamfeld came with the correct proof later. So this paper of Ginzburg doesn't have the proof of commutativity.
Yeah, it doesn't have.
So you cannot actually say that this. He talks about this monoid. So this Satake isomorphism didn't exist in that paper, really, because it didn't have a commutativity.
Yeah. So yeah, basically, he only talked about the constructible one. So. Yeah. Yeah. Also, but in that article, so Ginzburg provides a geometric proof of this fact. So this filtration defined by regular nilpotent gives the Q analog of multiplicities, and which is Ginzburg's proof is very different from Gupta's proof. So by the way, so when she published that article, so she used the name Brzezinski.
Okay. Thank you.
Thanks.
So I missed Raphael's remark about the we can still take an additive category in the constructible setting. I didn't understand what was being said then.
He said that so if we consider the direct sums of those power shifts, so power shifts inside okay, where is it? So here we can't define tensor product on this category. But so if we only consider the subcategory of direct sums of shifts of those parallel shifts, then we can define a tensor product, which will also give us. I guess that's his remark.
It's similar to what George Lustig does for perverse shifts on the quiver varieties, where you can look only at the semi-simple ones and you have this additive category and shifts or the whole category. I mean, it's also a question I was asking. I wanted to check that convolution of semi-simple shifted is still semi-simple shifted now.
I mean, it's even more miraculous that convolution. That's what George first showed, that convolution of semi-simples is semi-simple without shifts.
Yes.
But I think that you probably still need, I mean, if you want to define the monodal structure on the whole triangulated category, I would be suspicious if you could do it with only geo-constructible.
No, I don't think we can do it. But I think Hopf means that in a sub-additive category we can define a monoidal structure, I guess. Yeah, but I don't think so we can define a monoidal structure on the whole triangulated category. So because so just as some step of the definition of that convolution that doesn't work for the constructible setting. Yeah, but actually we can define a convolution between a equivariant shift and the constructible one, and we get a constructible one. So this is the module structure. We can define this.
Any other questions, comments? If not, let's thank the speaker again.